Professor Clements with you as we again consider cosmology. A study of the history of the universe is the main theme for this video. We would specifically want to see if we could answer the question, did the universe have a beginning, or has it always been here? And if it did have a beginning, what were the conditions? So I hope that doesn't give away the answer to the first question too much, but let's go on. So two competing theories from the middle of the 1900s. One would be the steady state theory, saying that the universe did not have a beginning, it's always been here. And as the galaxies move away from each other, there's continuous creation of mass, hydrogen atoms, that fills in the growing void between the expanding galaxies, expanding distance between the galaxies. So that's the steady state theory. The other proposal, called Big Bang, and actually the name Big Bang was a term of ridicule by the proponents of the steady state theory, but you probably have heard the name. But this is not an explosion, but rather an expansion of space, and with a beginning time of about 14 billion years ago. In the Big Bang, light becomes matter. We'll get to that more. The Big Bang, the universe starting off as light, and has a proposal that this light changes into matter. And there'll be a little bit more coming on that, but this is allowed with E equals mc squared. The energy of light can produce mass. As the early universe was starting off, the temperatures were extremely high and very violent collisions between the particles. Those collisions would rip off the electrons from the nucleus, so we'd have very heavily ionized material. And it turns out that having these free electrons not attached to a nucleus enables them to very effectively absorb light, to block light from getting one place to another, to absorb it. So that's in the Big Bang theory. And if we go to our next slide, as the universe expands, the expansion results in a cooling. Eventually, after something like 400,000 years after the expansion first starts, the free electrons join with the nuclei to form neutral atoms. And if you've been watching some of the videos in this course, you know that neutral atoms absorb light just at certain wavelengths. The absorption does not take place all the way across the electromagnetic spectrum. The hydrogen atom absorbs particular wavelengths, mercury atom absorbs particular wavelengths, helium atom absorbs particular wavelengths, so forth and so on. And there's just hydrogen and helium, basically, in this early universe. But before the electrons combine with the protons to form hydrogen, or with the two neutrons to form helium atoms, neutral atoms, this electron, free electron nature, is really blocking light from leaving the region where the electrons are. But we have this new arrangement now with the electrons combining with the nuclei to form neutral atoms, and the light can escape. The light can escape and can exhibit a redshift as the universe stretches space. The wavelength of this light is stretched, where it was in the gamma ray radiation realm in the electromagnetic spectrum when the light was first escaping, or last, just starting to escape, I should say. But the characteristic temperature of the universe, very hot, so gamma rays. But the redshift, the stretching of space, has lengthened the waves until now the peak of the spectrum of the cosmic ray, the cosmic background radiation, is out in the radio realm, the microwave realm, the radio realm, and it represents a temperature of about 3 Kelvin, and 0 Kelvin is our lowest temperature, absolute zero. So we have 3 Kelvin, and this radiation was discovered by accident in 1964. Penzias and Wilson, working for Bell Labs or AT&T, they were working on a big antenna to listen to microwaves reflected from satellites, trying to set up a communication system. and they always had static in their equipment. They couldn't figure out what was going on, where the static was coming from, and then they realized it was coming from everywhere. The whole sky, there is a cosmic static that we call the cosmic microwave background now. They couldn't get rid of it. They got linked in with theorists at Princeton University, I believe, and came to realize that this provided evidence of the Big Bang. So let's go a little further here. Here is the satellite dish antenna, a little bigger than satellite dishes you might see today, but a big horn to capture the weak energy expected from the satellites. And it was good that it was this big, because it was able to capture the weak cosmic microwave background radiation. And Penzias and Wilson there posing, looking at the big antenna. That's quite a nice story. You might want to research that a little bit more on your own. So that antenna gave some first measurements, some crude measurements of the spectrum for the cosmic microwave background. But better measurements have been made by satellites in orbit around the Earth, measuring this microwave radiation from the whole sky. So the Kobe satellite, 1989, when it measured the spectrum of the cosmic microwave background, this is a very good fit to the 3 Kelvin black body curve. So we have the data in the red and the black body spectrum for 3 Kelvin, approximately 3 Kelvin black body. So this was taken to be very solid proof that the Big Bang Theory was correct. The Big Bang Theory predicts this leftover radiation from the start of the universe. The steady state theory does not predict this cosmic microwave background radiation, not the simple steady state theory. Better satellite data comes in 2001 with WMAP, and then even better data with the Planck satellite in 2009, giving more details and more information. And some of this information here, so again, the most important part of these satellites is confirming the Big Bang Theory, confirming there is this microwave background radiation that's been greatly redshifted into the microwave realm from the gamma realm. But some other information from this data, the size of the variations of the blue and the orange here, and this is all false color, just to help to see the contrast and the difference in the data. There's actually very little variation, but this variation's been enhanced in this color photograph. And the scale, the angular scale of how big the variations are, the fluctuations, can give information on the curvature of the universe. And it turns out these fluctuations are around 1 degree, and that's the prediction that a flat universe would have for the cosmic microwave background and its variability. So that is matched, and as far as we know, we're not in a positive or negative curvature. We're in a flat universe. And you might want to go to these websites and look up some more information. If you're one of my students having access to the PowerPoint, the yellow here are actual links to these websites. So let's go back to the Big Bang. Starts off as light. The universe starts off as light. And that light is going to create matter and antimatter. So a little bit on antimatter. So we have anti-electrons that called a positron, and it has the same mass and other characteristics as the electron, but it has positive charge rather than negative charge. An antimatter proton would have the same characteristics as a regular proton, but it would be negative charge rather than positive charge. So antimatter. An interesting thing about matter and antimatter, if we take an electron and a positron, they come close to each other, the mass can disappear and become energy, get back to light. So that's annihilation. And as far as we know, there's no evidence that this is happening across the universe, that there are places where matter and antimatter exist and get close to each other and annihilate. We don't see that type of radiation from our universe. But it's always good to ask the aliens, are they regular matter or antimatter? And don't shake hands with them. If they're antimatter, you'll both explode. So here's the process of light, creating matter and antimatter. There's a law of conservation of charge. So when this light becomes mass, it has to create a positive particle and a negative particle. And these two particles won't go into it, but they will curve opposite directions in a magnetic field. The magnetic force is in opposite directions. So scientists can control the spread, the split here, and analyze the particles. And this is well confirmed in laboratories that light can become mass and form the regular electron on the bottom and the positron, the positive electron, shown in the top of the slide. So that's going on. The light in this early universe could create an equal amount of matter and antimatter. I have a question for you. Why is there only matter in our universe? The chair you're sitting on is regular matter. It's not antimatter. If you were regular matter and the chair was antimatter, you'd blow up. The terrific explosion. In our solar system, all the planets are regular matter. The comets are regular matter. The asteroids are regular matter. The sun is regular matter. We don't have any antimatter except in small quantities in laboratories for brief amounts of time. So why is that? And everywhere we look, the universe is regular matter. Well, the theory is that in this early universe, as there's this great mix of energy and particles being created from light and annihilating each other, there was a slight tendency, for regular matter to stick around more than antimatter. This antimatter, some of it in a complicated way that we're not going to go into, some of the antimatter changes into regular matter, and the rest goes back to light. So we live in a universe where the regular matter has survived. No, maybe we live in a universe of antimatter, and what we call matter is really antimatter. And that's semantics, it doesn't matter. There's one form of matter, we have it. There's another form, antimatter, with opposite sign charge on the particles, one basic difference. And that's only in small quantities, that antimatter. Our whole universe is matter. It's not a mixture with half of a galaxy being matter and half of it being antimatter, or one cluster of galaxies being matter and another cluster of galaxies being antimatter. There's no evidence that that's the case. Our whole universe is matter, and there was a shift, a slight preference for regular matter to form versus antimatter. Now, in those slides of the satellite data that I showed, there's those color variations are greatly enhanced. Think by a factor of about 100,000, the contrast. So it's very, very uniform, this cosmic microwave background. It's very, very uniform, implying that actually the universe was very, very small and then got bigger, inflated. With a small universe, the neighboring pieces can share temperature and energy and make this smooth variation of the cosmic microwave background. So at a time early in the universe, it was very small, and there was these energy fluctuations. We're delivering energy back and forth, and we get a very homogeneous universe. And then inflation took place. The universe got big suddenly. And it's not really well explained on why that happened, but to get to the size we have today, there needed to be a time of inflation. So that's about all I'll say for that. So if I can, I'm going to go to the next slide. Oh, this graphic is a little difficult to read, but we have the universe starting here in what's called the Big Bang at the expansion of space. I have light, and the universe is getting bigger and bigger, expanding. This cosmic inflation takes place, and we expand out to a more characteristic size of what we have today. And notice the time here, very short. 1 second, 100 seconds, 1 year, 100 years, and then 380,000 years. This is when we get the universe cooling to the point that atoms can form and be stable, the electron around the nucleus. And no stars yet, just atoms, the dark ages with no concentrated light sources. And then stars and galaxies form, roughly 200 million years. So a billion years, 10 billion years in 13.82. I think the number is 13.77 now for the age of the universe, and the way that we see the galaxies near us represented out here. But that would be kind of a timeline for the universe. A lot happening very fast in the early universe. Big changes, sudden changes occurring. And we're in a more region of gradual change now for where we observe the universe. But cosmic inflation, a way of providing for this very smooth cosmic microwave background, having the universe very, very small at first and then inflating more to the size that we see currently, and there's still expansion of space going on. So this graphic is a little misleading. You have to use your imagination. The space is getting bigger. They're just not represented here. They're just concentrating on events happening. So what evidence do we have that supports the Big Bang? Expansion of the universe. We see the galaxies moving away from each other. That sort of leads us to that there was some starting time. But the cosmic wave background, microwave background, this is the conclusive proof that Big Bang is right. Big Bang predicts this happening where the light is kind of trapped by the electrons in the early universe. When the electrons combine with the nuclei to form atoms, then the universe becomes transparent, and this light can get out. This light is redshifted by the expansion of the universe, and from the gamma rays into the radio spectrum, the microwave spectrum, where we see it now. Other evidence that steady state is not right. Steady state says it's the perfect cosmological principle, that the universe is always looking the same. And we see quasars in the past. We don't see quasars now. The galaxies are close to us. Other active galaxies, same thing. The Big Bang also makes a prediction on how much hydrogen, helium, and there are a few other elements, lithium, beryllium, that are created during the Big Bang. Astronomers can measure this abundance in very distant gas clouds that are near quasars. When that quasar light goes through those gas clouds, absorption lines are created, and the astronomers can measure the abundance of hydrogen, helium in those gas clouds, and the data shows a match with the Big Bang theory on what the Big Bang says will be produced for the percentage of hydrogen and the percentage of helium. And I think I've got that someplace here. So it's around 75% hydrogen, 25% helium. At least you should know, my students should know, that there's more hydrogen than helium produced in the Big Bang. So I'm not finding that here in my source, but that's my memory. It's about 75% hydrogen, 25% helium, and then just a smattering of other things. Yeah, and that's by weight. Those percentages by weight, not by the count of the atoms. So you might want to generate a list of questions, and we're dealing with the universe, the whole universe, so the ultra deep field, the Hubble telescope, all these galaxies here, expanding outward as a result of the expansion of space. And outward is just a little misleading. Space itself is expanding. Astronomers are not looking for some center position. But I do want to come back to sort of this diagram at work here. The universe starts off as light, and for my students, and possibly in other classes as well that might be listening to this, a little opportunity here to talk about science in the Bible. And this will not be on the tests I give to my students, but I'm very comfortable with the coexistence of science in the Bible. I believe the Bible is true and that there was a beginning. Genesis agrees with the Big Bang, or Big Bang agrees with Genesis, whichever way you prefer to word that. But in the beginning, there was light. So, that's Genesis chapter 1, verse 1. In the beginning, God created the heavens and the earth. The earth was formless and empty. Darkness was over the surface of the deep. The Spirit of God was hovering over the waters. And in verse 3, God said, "Let there be light," and there was light. And we go on through the creation of described in Genesis, not as a science textbook, but as kind of a pattern. And I am comfortable that the universe is 13.77 billion years old. Time is not a problem. 2 Peter 3:8. Just read you that passage. Do not let this one fact escape you, beloved, that with the Lord 1 day is 1,000 years, and 1,000 years is 1 day. I believe God created light, created matter, and created time. And God is patient to a point, but this 13.77 billion years is not a problem for believing in God. And there are other passages as well. I'll let you research those on your own, or ask a pastor that would be comfortable in discussing this with you. And Big Bang, Bible, I think are in line with each other. The universe had a beginning, and this beginning was a universe of light, and then we get matter forming, and God creating all the physical laws that then the universe follows and comes to have the form we have today. Hope you enjoyed that little sidetrack. Again, for my students, the Science in the Bible portion will not be on your exam, but something worth thinking about. So ask your instructor some questions.